Okay, this video specializes on sample space, and I'm just going to tell you it's one of the most important topics in basic probability. It will help you solve some very difficult problems. It'll make some problems that are seemingly impossible accessible. Truthfully, it requires a fair amount of work, but if you do the work, if you actually set up the work and set up the sample space, the problems become accessible and you can get them right, which is going to be really important in the probability section. So when do you create a sample space? Well, we've been doing it before by doing our blanks. But whenever you are doing something that is played twice, or something that is done twice, or you have two of something, it is very, very helpful to set up a sample space. So let's start off with the basic rolling a dice. What's the probability of rolling a fair six-sided dice twice? So there's my word, and getting a sum less than 8. Create a sample space to answer the question. Well, I'm going to show you how to do that. And I'm actually going to take the time away from the video and actually do that off to the side, because I recommend that you do this at least 3 times the day before the test or the day of the test prior to taking your test, so that it just gets ingrained, becomes very easy and fast. So you start off by 1, 1. So I can get a 1 on the first roll, a 1 on the second roll. Then I can get a 1 on the first roll, a 2, and then a 1 on the first, a 3 on the second. And I just go like that: 1, 4, 1, 5, 1, 6, 2, 1, 2, 2. And by now you're groaning, and so am I. This is not something I enjoy doing, but I do know that I will get problems right very easily because of it, and I'll eliminate a lot of careless errors. And although people worry about the time it takes to do this, it takes less than a minute. If I told you that if you spend a minute on a problem, then you'd have 30 seconds to answer the question. You're like, oh, that's only a minute and a half. And I said, and you're almost guaranteed to get it right. I think you would do it. So there's my sample space. And basically I have what I have here. And that's all the more I need to draw. It says, what is the probability of rolling a fair six-sided dice twice and getting some less than 8? Well, less than 8. 2 plus 6 is 8. 3 plus 5 is 8. 4 plus 4 is 8. 5 plus 3 is 8. 6 plus 2 is 8. So that's 8. But I want less than 8. Well, 1 plus 6 is 7. 2 plus 5 is 7. 3 plus 4 is 7. 4 plus 3, 5 plus 2, and 6 plus 1. So all of those that I just circled are less than 8. Well, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. And so basically the answer to this question is 21 out of, well, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6 out of 36. So 21 out of 36. Of course, we could reduce, but for the time being, that would be the answer to that question. Then it says, given the sum is less than 8. Well, we already did that part. We found out that, and remember, given is always in the denominator. So it's intersection over given. And it was like, oh, well, we have 21 that are less than 8. What's the probability the sum was equal to 5? There's the ones that are equal to 5. So 1, 2, 3, 4. So in this case, 4 out of 21. All right, the next one, it says, given the sum is less than 8, what's the probability that the sum was greater than 4? Well, once again, we know given goes in the denominator and the intersection's on top. And we know that we counted these up and said, oh, there's 21 that are less than 8. But now I need to look at greater than 4. Well, 1 and 3, 2 and 2, 3 and 1. That's my 4. So I need this group right here. And remember, the intersection's often the parts that circle twice. And if I were to count these up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 out of 21, because 15 of them have a sum that's greater than 4. 1 plus 4 is 5, 2 plus 3 is 5. So these are the ones that are greater than 5. All of these that were circled were greater than 5, but had a sum that were out of the group, the sum less than 8. The next one. What is the sum? Given the sum is less than 8, what's the probability the sum is 3 or less? So once again, we have given in the denominator and the intersection on top. We counted these up before and said, okay, there's 21 of them. And it says sum is 3 or less. 1 plus 2 is 3, 2 plus 1 is 3, and or 2 is also less. So we have 3 out of the 21. So that's where that comes from. But then we make the problem a little more difficult. What if the dice had been weighted and the probabilities were as follows? So no longer is it a fair die. The probability of getting a 1 is 10%, the probability of 2 is 10%, probability of 3 is 10%, probability of 4 is 20%, 5 is 20%, and 6 is 30%. And by the way, I should check these out and see that they sum to 1, which they do. It says calculate the probability of doubles. Where does doubles occur? And I wish I had a clean one, but doubles occurs here. I'd have to get either a 1-1, a 2-2, a 3-3, a 4-4, a 5-5, or a 6-6. So if I have to get a 1-1, what's the probability of getting a 1? Oh, we said 10%, but I have to get that twice. So that's 0.10 times 0.10. Or I could get a 2-2. Probability of a 2 is 0.1 times 0.1. Probability of a 3-3 is 0.1 times 0.1. A 4-4, 0.2 times 0.2. A 5-5 is a 0.2 times a 0.2. And then they also have to get a 6-6, which is a 0.3 times 0.3, which is what this table shows. 0.1 squared plus 0.1 squared plus 0.1 squared, 0.2 squared, 0.2 squared, 0.3 squared. And the squared just because it's the 0.1 times 0.1. All right. So our probability in this case would be, the probability of doubles would actually be 0.20. All right. Calculate the probability the sum equals 6. So it says calculate the probability the sum equals 6. So I need to look up at my table and go, where does it equal 6? Well, 1 plus 5 is 6 and 2 plus 4. So basically, this group right here ends up equaling 6. And we remember we have a weighted die. So we're looking at a 1-5. We're looking at the 2-4, a 3-3, a 4-2, and a 5-1. Probability of getting a 1-2, the probability of getting a 1 is 0.1. We also have to get a 5, which happens to be 0.2. The probability of getting a 2 is 0.1, but the probability of getting a 4 is 0.2. The probability of getting a 3 is 0.1, and we have to get another 3, which is also 0.1. We have to get a 4, which is 0.2, and then a 2, which is 0.1. And finally, we have to get a 5-1. Probability of a 5 is 0.1. I mean, excuse me, 0.2. And the probability of the 1 is 0.1. So that's what we got here in this table. 0.1 times 0.2, 1 times 0.1 times 0.2, 0.1 times 0.1, 0.2 times 0.1, and 0.2 times 0.1. So the probability that the sum would equal 6 is 0.09. Okay. Once again, really that is a very challenging problem. But if you make this table and then come back and go, okay, What are my combinations? And plug in the probabilities, you can do that. All right, so it becomes accessible. Here's another very challenging one, and I can assure you there'll be something similar to this on the test. A game of chance is played in which the number of points scored in each game has a distribution shown at the right. What is the sampling distribution of the sum of the scores when the game is played twice? So they said sum and played twice. So I know this thing is happening twice. So consequently, I'm planning on having to make some sort of table for this. But let's make sure that we can interpret what they're asking. First off, there's a 0.3% chance, there's a 30% chance that I get 0 points. There's a 40% chance I get 1 point, and there's a 30% chance I get 2 points if I play the game once. So I can get either 0 points, 1 point, or 2 points with the following probabilities: 0.3, 0.4, and 0.3. So let's go ahead and take a moment and let's make a sample space for what could happen. The first game I play, I could get 0 points. In the second game, I could get 0 points. Then 0 points for the first game, 1 point for the second. 0 points for the first game, 2 points. 1 point for the first, 0 for the second, 1 for the first, 1 for the second, 1 for the first, or 2 and 2 for the second. I could get 2 points the first game and have a bad second game and get no points. 2 points to get 1 point, or I could get the maximum, which would be 2 and 2. Now they said we're going to sum. 0 and 0 sums to 0. These actually sum to 1 point. This group actually sums to 2 points. This group sums to 3 points because 1 plus 2 or 2 plus 1. And there's only one way to get the maximum, which is 4 points. All right. So I've written these probabilities down. And you're like, well, how did you do that? Well, first off, I need to make a correction here. This should say 0.4 times 0.4, which is 0.16. This needs to scratch out and become 0.16. That equals 0.34. All right, so the probability of getting 0 points on the first roll, 0.3. But I have to get it twice, so 0.3 times 0.3, because that's my 0, 0 right there. There's my 1, 0. That's getting a 1 on the first and a 0 on the second. So basically, I filled in all those probabilities for you, and that's the probability of all the combinations. The probability of getting 2 is 0.3, but I have to get it twice in order to get 4, all right? And I added them up. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 2 is 2. These are my 3s, and these are my 4. So my probabilities are as follows. This one and this one sum to 24.24. And then 0.09 plus 0.16 plus 0.09 gives me 0.34. This plus this gives me 0.24, and this plus this gives me 0.09. This is a difficult problem. You will need to practice it, and you may need to come ask me questions about it. But once again, if you will set up the table and go, okay, there's my sample space, 0, 0. Well, what's the probability of getting a 0? 0.3. Oh, I need a second 0, so 0.3 times 0.3 gives me 0.09. That's the only way I got 0 points. With 1 point, I could get 0 on the first and then 1 on the second, or 1 on the first, then 0 on the second. 0 on the first, 0.3, 1 on the second is 0.4, 0.3 and 0.4. Or 0.4 on the first and then 0 on the second. And that's the way the table is built. All right, thank you.